Good afternoon, everyone. And on behalf of US Microproducts, welcome to our webinar. My name is Brian Wilkie. I'm advisor to the CEO of US Microproducts. I used to be the COO until I decided to spend a little bit more of my time with my grandkids and my golf. My grandkids are doing fine. My golf is not doing so well. So let me start with an introduction to US Microproducts. We design, build, and deliver engineered display solutions. So we're not an engineering firm. We actually ship product. We've been doing that for some 25 years. And we have something of an advantage over most of you in that we design hundreds of display solutions every year. So we've learned quite a few of the tricks of the trade. We're US based in terms of sales and customer service, and we have a Taiwan team who look after design, interface with our supply chain, and we have quality engineering in that team. We are agnostic when it comes to display technology, shipping LCDs, passive matrix OLEDs, active matrix OLEDs, and most of our stuff these days has a built-in touch solution. Today we're going to go back to the basics of what is glass, and then talk about how some of the treatment that we can give to glass to make it tougher. We're going to break some glass in ball drop testing. And then I talk about why we polish edges and why the edge is important. And then we're going to talk about different surface treatments that you can give the glass to keep your product looking better for longer. So let's, like I said, go right back to the basics. What is a cover lens? Well, displays are actually pretty complex beasts. There's a couple of polarizer layers. There's a layer of glass, which is the touch sensor. And then the LCD itself, which is actually two layers of glass with the liquid crystal between them and some spacers. And generally, there are a couple of layers of optically matched special adhesive. And then right on the top of that, on the outside, is the cover lens. And the cover lens's job is to make your product look good and keep looking good over the life of your product. So what is glass? Well, it's mainly sand, silicon dioxide with some soda and some lime to lower its melting point, and a few other minerals thrown in. That's known generally as soda lime glass. And it's all melted and stirred together. And after melting, it's cooled too rapidly to form crystals, because it turns out that crystal boundaries are what stops most materials from being transparent. So glass is actually an amorphous solid, kind of like, but not exactly, a supercooled liquid. And interestingly enough, it's made into sheets by floating the melted glass onto a layer of molten tin. So soda lime glass is what's usually used on cover lenses, and it's usually the most economical solution. It's basically the same stuff that's used in your windows, but much thinner and much higher quality ingredients and production values, because it has to be optically perfect. It can be used as thin as around 0.5 millimeter up to about 4 millimeters in thickness. Interesting fact is that if you take a piece of window glass and look on the end so that you're looking through a long depth of glass, it's going to look green. And that's caused by iron impurities in the original sand. So some of the time we use white glass, which uses very low iron ingredients to avoid that color cast, because one of the things you don't want anything in your optical system to do is take away from the color rendering of the display itself. There are other options, generally either a lot more expensive or quite a bit more expensive, like sapphire and borosilicate glass, silicate glass. So there are other options, but soda lime is what most people use most of the time. And the trouble with glass is it breaks. So why does glass break? Well, it turns out that glass is stronger in compression than in tension. So stretching glass does more damage to it than compressing it. So when you bend a sheet of glass by doing something like dropping a steel ball onto it, it really does bend. And the problem is that on the outside of that bend, the surface is stretched. And if it stretches enough, the stretching exceeds the tensile strength of the glass, and it breaks and it's gone. Luckily, there are a few things we can do about that. One of them is to heat treat the glass. The way we do that is we take that sheet of glass and we heat it to about 1200 degrees C. It expands for us, and then we cool it pretty violently with air jets. And what happens is that surface freezes at the expanded size, but the bulk of the glass continues to cool, and it contracts as it cools more slowly. And the effect of that is it puts a compressive force on the surface layers of the glass that froze earlier at the larger size. And that force can be up to about 10,000 pounds per square inch. So it's a pretty impressive amount of force that you can apply to the surface of that glass. So now when we drop another steel ball, when the ball lands and the glass bends, the tension from the bending is less than the compression due to the heat treatment. So what happens is the ball just bounces. We have significantly strengthened the glass. Interestingly enough, if you try hard enough, you can still break tempered glass. And unlike regular glass, which breaks into shards, which are actually pretty dangerous when they're flying around in the wild, tempered glass, because of that physical energy that's stored within the glass itself, breaks into very small fragments, generally roughly cubical in size and fairly small, and that makes for a much less dangerous breakage, in fact. And so if you're making things like shower enclosures, you use tempered glass, because if you do break them, they're much safer. In fact, when we do failure analysis on displays, one of the ways we can check whether the heat treatment was done properly is by examining the size of the fragments that result after breakage. So there are a couple of different ways to do this. If we just heat it and then cool it rapidly, we get something that's basically 2 times stronger than regular glass. But because of that embedded energy within the glass, you can't cut it after that heat treatment. So you cut the glass to size for your final application and then heat treat it. If you go further and heat it to around the same temperature but cool it very rapidly, you can get something that's 3 to 5 times stronger than regular glass. Again, can't be cut after heat treatment. And that's what shatters into the very small pieces. Because of the amount of thermal shock that's applied to the glass during this process, it really has to be around about 3 millimeters or thicker. Otherwise, slight irregularities in the cooling on either side will cause it to distort and not be flat any longer. So you need relatively thick glass for that heat tempered solution. And the trouble with that thick glass is that it's heavier. So Corning came up with something that's known as Gorilla Glass, and it's actually chemically strengthened. So what you do is you put that sheet of glass into a bath of primarily potassium salts at a few hundred degrees centigrade for long enough and with high enough salt concentration. Then what happens is those potassium ions in the liquid exchange themselves with the sodium ions on the surface of the glass. And it turns out that potassium ions are significantly larger than the sodium ions they've replaced. So that actually gives you the same kind of surface tension, the surface compression on a very thin layer on the surface of the glass. And that again gives you compression, which makes it stronger. It also makes it more resistant to scratching, which is a good thing, and gives you the same kind of strengthening effect as tempering, but you can do it on much thinner sheets of glass. You do have to be careful because there isn't the same amount of stored energy in the glass, so it will break into shards just like regular glass. Of course, the cover lens is not the only component in the display module. And one of the interesting things that happens is that when you join things up, you make a stronger assembly. Used to be we used something called air gap bonding, which is basically a double-sided tape used around the edge of the display to attach the cover lens. We don't do that so much any longer for a couple of reasons. First of all, internal reflections can cause loss of contrast, particularly if you're using the display outdoors. And the other effect is that each layer can flex separately. So they're not as stiff as a system which uses optical bonding. And optical bonding uses an adhesive which has the same refractive index as glass. So light is bent the same amount in the adhesive as it is bent in the glass. And so it's optically transparent with no visible join between the layers. And that causes the entire assembly to react as one piece, which is much stiffer than any of the individual components. And so it gives you a really strong and optically pleasing stack of display and cover lens. But we still like to break things. And how do we do that? It's called the ball drop test. So we take a 2-inch or 50 millimeter steel ball, which weighs about half a kilogram. We guide it to its target with a vertical plastic pipe. We usually hold it on a magnet until we're all lined up and then let go and drop it from around 400 millimeters onto the display. It's important that the display is held in the final housing that it's held in, because the mechanical setup around the display is an important part of the mechanical response of the system. And there's a There's an international standard which assigns 1K ratings according to the amount of energy you put into the ball drop. And so IK07, which is what most systems like to achieve, uses an energy of about 2 joules, which is what you get when you drop that 0.5 kilogram steel ball from 400 millimeters. So let's take a look at what that actually feels like when it gets done. So we're going to take a 19-inch display. This one has an air gap on it, and we're going to drop a steel ball from 36 inches in this case. So here's the setup. Everyone's standing right by, and you really need to see it in slow motion. When the ball hits, the glass tries to flex and then just shatters. And there are small fragments of glass and big shards of glass flying around inside the system there. So pretty messy. However, if you do it on an optically bonded display with cover lens, then when the ball drops, it's much less spectacular. And watch for the flexing of the glass. You'll see it bounces like a sheet of plastic. Glass is not really as rigid as you typically think it is. So that ball just bounced. And let's look at them together. There's the air gap versus the optically bonded. Quite a difference in performance. And actually, it was pretty difficult to find a good video of this, because most people, when they demonstrate ball drops, want to demonstrate how strong their display is. So thank you, GM Nameplate, for providing that video. The next thing we have to worry about in the system is the edge. Any scratch or crack in the glass acts to concentrate the stress, and so the stress on the end of the crack is just like the blade of a knife. It's a lot higher than the pressure on the knife itself. So concentration of stress is not a good thing. And cracks on the edge are particularly nasty because there's no glass on the other side of the edge to balance the compression force. So as you cut glass, it's pretty important that you have a nice smooth edge. And there are a couple of ways to do that. If you saw cut the glass edge, then there's some significant shards on that top edge, as well as the saw marks down through the edge. Laser scribed is more expensive, but it gives you a much cleaner cut. But there are still some very small shards on that top edge where the laser first hits the glass. So what we do with cover lenses is we polish the edges, and the polishing takes off those minor chips and cracks and significantly increases the strength of the overall system. If you really want to have an air gap display, we can add a plastic anti-shatter film on the inside so that the glass fragments don't fly around. Optical bonding operates the same way and also gives you a much stiffer structure. So it's significantly stronger than air gap bonding. Other elements of the cover lens is the printing on the inside layer of that cover lens. We generally print a mask layer to mask off the unused display areas. We print logos on there, and we have to be pretty careful about the ink that we use for outdoor applications, because normal inks over time, when they're exposed to enough ultraviolet radiation, the bond between the ink and the glass surface degrades over time. Takes a few years, but it doesn't look very nice after a few years. So for outdoor use displays, we use very special inks which are designed to be UV resistant. If you are in a really sunny environment, then a better solution is ceramic ink. And that's actually printed onto the inside layer of the glass and then baked so that the ink is actually absorbed into the surface of the glass. And that is really resistant to UV degradation. However, it's not going to work on chemically strengthened glass because it would mess with the chemically strengthened process. So not an option that's available to you. On the front surface, there are multiple tricks that we can take advantage of to improve the performance and the appearance of the system. First of all, anti-glare treatment. That effect when there's a strong light behind you, and the glare just reflects off of the surface, is not very pleasant, and it can interfere with the readability of the display. So what we do is we put very small undulations on the surface, and that breaks those reflections up into multiple directions. It's very effective in reducing glare. You have to be careful about how much of that you do, because you can lose some of the resolution of the display if you do too much anti-glare. Sometimes we do that as an applied film, but we really prefer to do etching to cause that surface undulation, and we can actually dial in different amounts of anti-glare. And there's a fancy machine that measures the gloss of the surface, and it turns out that a lower number on the gloss reading means less glare, but more impact on your resolution. So how does that actually work? So a ray of light strikes the surface of a flat sheet of glass and reflects off. Some of it is absorbed, but a lot of it reflects off. And if your eye happens to be in the direction of that reflection, then you're going to see that as a glare. What we do is we add some surface undulations, and as that ray of light strikes the surface, it gets reflected in multiple directions. And each of those directions is significantly less bright of a reflection. So really makes a difference in the system. The other technique is a bit more scientific. We can give an anti-reflective layer on the surface of the glass, and we use something called chemical vapor deposition to lay down several layers of material on the glass. And we need several layers because each layer is tuned to a different color of light. So you need typically 3 or more layers to cover all of the wavelengths of light that can arrive. Each layer causes reflected light of one color to cancel itself, which hugely reduces the reflections. But light coming from the inside of the display is not affected, so it comes straight through. And these are all surface coatings, but they're pretty hard and so reasonably durable. So I'm going to give you a physics lesson here. Light is interesting. Sometimes we deal with it as particles, and sometimes we deal with it as waves. So this time we're going to deal with it as a wave. And there's that wave of light coming down to get reflected off the surface. So it gets attenuated a little bit by that reflection, but goes straight back out towards your eye. If, however, we add another layer that turns out has to be half of the wavelength of the light that's coming in, then what happens is light gets reflected off the original glass surface and off of the top of that layer. And those two reflections are exactly half a wavelength apart from each other. So they cancel each other out. And what your eye sees is more like this, a much reduced reflection. You do that with a few layers so that you can cover red, green, and blue light, and you end up with a very nice anti-reflective effect on the glass. Fingerprints, of course, are pretty nasty, and we actually have some technology to deal with that. Anti-fingerprint coatings can be sprayed onto the glass surface, and what they do is they prevent anything you put onto the surface from actually wetting the surface. Anything on the surface is more like a ball than a spread out piece of liquid. And what that does is it makes those fingerprints easily wiped off. And so it's very easy to clean something that's had anti-fingerprint coating on it. It also has a side effect in that touch systems, you really want to be able to use gestures. And the anti-fingerprint coating actually allows your finger to slide more easily over the surface. So it's actually pleasant to use on a touch-enabled system. And if you're in the medical business, then an interesting surface treatment is antibacterial. By using the same kind of process that's used for chemical strengthening, you can add copper or silver ions into the surface of the glass itself, and one of the effects of copper and silver ions is they disrupt the films on the outside of a bacteria, or indeed of a lot of viruses, and so that process gives you a pretty effective antibacterial surface on your glass, which is pretty important in medical systems. So lots of choices. One of the things you have to be careful of as you make those choices is just how hard is it? And 150 years ago or so, someone called Mo came up with a measurement system for measuring the hardness of surfaces. And just to calibrate you, lead pencils are 2H to 3H. Diamond is 10H. It turns out glass is about the middle, around about 5 or 6. And what you do is you have pencils of a defined sharpness, and you test the surface with a harder and harder material in the pencil. And once you get to one that doesn't scratch the surface, that's the hardness of that surface. So both thermally treated and chemically treated strengthened glass is significantly harder than regular glass, which helps the robustness of the system. And of course, plastic films are significantly softer. So you need to take a look at how those surface films are specified and how hard you get. Okay, so let's try and draw this to a conclusion. You have lots and lots of choices in designing the cover lens for your project. And just how you make those choices is really important, not only to how your product looks when it first comes out of the box, but it makes a big difference to how your product's going to look in 3 or 4 years' time. So making those choices is can be challenging, and making the right choices has a big impact on how your product is perceived. So we can help you steer through those choices. We are really happy to set up meetings to advise you on how those choices impact your design. So contact us at sales@US Microproducts, or call your favorite USMP sales contact to enlist our help. We are really happy to do that. So thank you for sticking with me through that physics lesson. Let's open this up to questions. If I can persuade my cursor to go to the right place. There we go. Okay, question from Eric. He liked my ball drop test, but nano indentation hardness and indent resistance. Yes, those are also valid to specify the cover glass performance. Those do more to measure how easy is it to damage the surface, which then makes it more vulnerable to physical damage later. So those tests are somewhere in between those pencil hardness tests and the rather destructive ball drop test. Aaron is asking, does anti-glare etching reduce the durability and resistance of the glass? And the answer is actually the etching is pretty benign, and you can actually chemically strengthen glass which has been etched. What you do is you etch it first and then chemically strengthen, so that the chemical strengthening goes over and around those indentations in the glass surface itself. So you just have to do it in the correct order. Okay, Anti-Voigt is asking, anti-fingerprint, does this work with common cleaning wipes and detergents? And the answer is that yes, generally the surface will survive cleaning. It's not going to be as durable over a number of years as something like anti-glare etched surfaces. So there is a lifetime to it, but it's the modern anti-fingerprint coatings are fairly robust. Okay, Adrian's asking, what's the most relevant metric to characterize anti-glare? There's actually a couple of machines that are generally used to measure the anti-glare property. So as we specify the amount of anti-glare, we'll probably specify the machine that it's tested on, and that gives you a standard of measurement. And like I say, there are a couple of popular devices that make that measurement. Okay, Graham is asking, can I talk about edge treatments with respect to IK ratings? And I'm not sure. I'm not sure that I can answer that off the top of my head. I do know that that polishing is important, and I'm not sure that I could off the top of my head tell you how much difference the polishing makes to the IK rating. I can try and get an answer for you, Graham, and get back to you. Okay. Matt is asking, can you hot form chemically strengthened glass? And the answer is yes, you can to a certain extent. You have to be careful about that. So you can do it, but do it carefully, please. And we can talk to you in detail about your needs. And Matt is also asking what technology we would use for a 27mm radius. You mean on the corner cut of a cover lens? I would use laser scribing for that. It's a bit more expensive, but you can do some pretty nice edge effects and curves if you use laser scribing. Okay, Patrick, give me just a second to read this. For tempered glass with 3mm, are you saying that the AR, AG, and AF are all included in the process? No, generally they're not included in the process. Those are options that you can add. Okay, and you must be in the automotive business because you're worried about homologation and presumably crash test. Generally, the tempered glass is much better for any kind of crash situation because of those smaller fragments that are generated, and even those fragments will generally be contained by the optical bonding material. And yeah, okay. Cost, that's a question for our sales team. I don't know how to answer it. I know that air gap is the cheapest, but the specifics vary hugely from display to display. So we're going to have to get back to you with that one. And Jim is asking, can we have anti-glare and anti-fingerprint on the cover glass? And the answer to that is yes, we can. Okay, just give me a second to get my cursor onto the right place here, and we'll see if we can't get on to the next question. Okay. Premchan, whether glass touchscreen capacitance with display requires glass or plastic or combination of both. Okay, capacitive touch is generally done on a glass layer. So you can certainly do it on plastic, but for most applications we use a glass capacitance touch sensor with ITO or indium tin oxide as the transparent electrode on that. So as long as you're not looking for a fancy curved screen, then glass works just fine for capacitive touch. Void, I'm not sure that I can answer that edge finish question. So let me get back to you on that one. And same with your your question, Jerry, on how small the internal radius on an edge be and still be polished. So I'll get back to you with that. And at that point, we've been answering questions for a while now. And I think this might be about the last one. So, okay. No, there's quite a few more. I think we should wrap it up now. We'll try and get back to you with answers to those questions that are remaining. So I think what we'll do is we'll go back to the final slide and say thank you for hanging with us. It's been fun talking to you, and I hope this was useful to you. And let me reiterate, we're happy to deal with detailed questions and sit down and have a meeting with you and go over the options for your particular circumstances. So thank you very much, and have a great rest of the afternoon.